The next question is to calculate the electric field intensity at a point away from two identical charges. And what's interesting about here is that the question is clearly given that the distance from the two identical charges is 10 centimeter. So the situation is such that the point P is at a location 10 centimeter away from both of our identical charges. So that's the situation, that's the calculation that we have to accordingly do. And of course, both the charges are also separated by a distance of 10 centimeter as well. So this is the situation which we have to factor in when we are making our calculations as well. So naturally here, what happens here for electric field intensity is that we have to add the horizontal and vertical components separately to make sure that such a figure is possible. So since the sides of the right angle triangle are 10 centimeter, this means that the triangle that I'm looking at is an equilateral triangle, and hence the angle is 60 degrees. So when I'm trying to resolve my components, I don't have to worry much because it's 60 degree here, 60 degree with respect to each of the axis. Whereas for P, right, for the positive x-axis as well, some at point P, the angle made will be 30 degree. 30 degree. Yeah, that's also going to be 60 degree as well. So that's how a 60 degree are going to be created here as well. And now I can start resolving the vectors one by one as well. So in fact, what am I going to do here? In fact, I'm going to start resolving for the particle. So one particle I'm going to name it as A, and the second particle I'm going to name it as B. So naturally, electric field due to A on point 1 is going to be like the value. There's going to be a fixed value for electric field. The electric field of A due to P. This is the component that I have to like completely, resolve into two components depending on the x and y component as well. So 100 microcoulomb, kq by r squared is a formula, remember, and r is of course 10 centimeters. So 10 centimeter is like 0.1 meters, so 10 to the power minus 2 after I squared it, right? So I'll just retain this value just for posterity's sake because it's going to be easier later down the line. Then E is BP is also going to have the same value, k into 100 mu by 10 to the power minus 2. So I have my correct values of electric field as well. Now I can start resolving these vectors as well, because I have to resolve these vectors and find the resultant. Naturally, only finding the resultant will give me the final solution over here. So what should I proceed here with? I should start proceeding with finding out the horizontal and vertical components of both these values here. Now in this case, we'll have horizontal and vertical components for both EAP and EBP as well. So naturally, the horizontal and vertical components are going to be defined by cosine for horizontal and sine theta for a vertical as well. So now when I start taking the values, right, EAX, so the sum of all the x components here in the x direction is going to be EAPX plus EBPX. And here's something interesting is going to happen, because you can see already, right, the values are already the same, right, but the angles are in fact different. One is a positive angle and the other is a negative angle. But since it's sine, right, since it is sine, both of them are since both of them are cosine angles, and cos negative angle is the same as the positive angle, both of them are just going to get added up. So I can like multiply it here and write the final answer right here itself, 10 to the power minus 4 plus 2 from the denominator. I'm bringing it up, so that's how I have my final answer. 18 into 10 to the power of 7, 18 into 10 to the power minus 7 Newton per coulomb is the value for the x component. While interestingly, for the y component, what's going to happen for the y component when I am going to like find the value of y component here, when I try to sum those values here for the y component as well, what's going to happen here is that the sine angles, when I take sine 60 and sine of minus 60, they are going to start cancelling each other, because sine of a negative angle is sine of minus theta is minus sine theta, right? Hence, that will result in the vertical components cancelling each other out. vertical components cancelling each other out, which will result in only one value, right? Remember, one values will get, there are two sine components pointing upwards, while one sine component pointing downwards. They will both cancel each other out. That's going to give us, in fact, only one value of the one value here. So it's just going to be 9 into 10 to the power 7 Newton per coulomb. So I have both my x components and my y components. Now I'm ready to solve for the triangle that I have. Remember, if I have the x component and the y component, I can just apply it in Pythagoras theorem and find the final answer. So I will square them. 81 plus 18 squared, which is 256, 289, 324, and 10 to the power 7 squared is 10 to the power 14. So you have that stuff sitting outside here, and we will simplify that right now. 4 plus 1 5, 404, 405, so somewhere close to around 20, right? So yeah, so this means the total electric field, the net electric field due to this value, square root of 405. We'll just check what the square root of 405 is. Thank you, Google, for the quick calculation. And it's 20.12, just like I predicted. So 20.12 into 10 to the power 7 Newton per coulomb is the net electric field at this object. So we have solved the problem for electric field intensity at a point away from two charges, in which you have to calculate for the x and y components separately, so that you will be able to solve the problem for the final answer.